Wednesday by midnight. It's already up and posted. So this is going to be the review. We're going to be going over sorry, I was trying to record. The practice problems that I posted. So practice problems for exam 2. So I have the first several already up here, and I'm just going to go through them. And when it gets to the actual problems that we need to solve for, I'll show you how to work through those as well. Now, I have a practice exam posted on Blackboard, and I recommend you take that as many times as you need to get them all right. The reason that I have the practice exam up there, it's not worth any points. What it's for is so you can see the type of problems. So when you get to the exam, you can focus on how to solve them and not worry about how do I enter the correct answer. Because I know for the homework, a lot of people were having troubles using the new functions, trying to get a superscript and things like that. So I wanted you to have the opportunity to see what format I'm looking for the answers to be in, so that when it comes to the exam, that's not something you have to worry about. So let's look at these practice problems. So the first one is just asking who came up with the original version of the periodic table, and that was Democritus. For number 2, name 3 ways in which the periodic table is arranged. There's more than 3 ways. I just wanted you to get you thinking about the different ways it's arranged. So one way is the increasing atomic mass. Okay, that's that average atomic mass that we see underneath the element symbols. It's also arranged in order of increasing atomic number. So if you remember atomic number, this is the number of protons as well. It's also organized by groups. So we have the alkali metals in the first group, and the alkaline earth metals in the second group. We have the transition metals in that D block in the middle. We have the halogens in group 17, and then the noble gases in group 18. So that's another way it's arranged. If you want to look at it in the sense of metals, semi-metals, and non-metals. So we have that staircase, that zigzag line on the periodic table that separates the non-metals on the right from the metals on the left. Anything touching that zigzag line, with the exception of aluminum, is a metalloid or a semi-metal. So that's yet another way. It's arranged by number of valence electrons if you're looking at the representative elements. Group 1 has 1 valence electron, group 2 has 2, so on and so forth. So many different ways. So let's look now at number 3. So number 3 is asking what 3 subatomic particles make up an atom. Okay, so subatomic. So we're talking about the protons, the neutrons, and the electrons. Okay, now the protons and neutrons are located in the nucleus. Remember, the protons have a +1 charge. That's why they're represented by this P+. Neutrons, neutral, no charge, so that's why N with a 0. So since we have plus charges and neutral charges in the nucleus, the overall charge of the nucleus is positive. So we have this positively charged dense center, and then we have the electrons, so that's the 3rd subatomic particle, orbiting around that positively charged nucleus. The electrons are negatively charged, that's why the E-, so they're attracted to that positive center. Opposites attract. So moving on to number 4. Number 4 gives you magnesium-25, and what it's asking you to solve for is how many neutrons. Okay, so remember, this is an isotope. This is one way that we can represent an isotope. And isotopes are atoms of the same element with different mass numbers. So when we represent an isotope this way, we have the element name, magnesium in this case, and then dash, and what comes after the dash is the mass number. So that 25, that's the mass number of that isotope. So if we needed to calculate the neutrons, we would need to know what the mass number is made up of. And the mass number is the protons and neutrons, because remember we said electrons, their mass was so small that it's negligible, so we don't count it towards the total mass. We counted electrons as 0. So it's just protons and neutrons that matter. Okay, well looking at this, I have the mass number that's given to me in this representation, 25. The number of protons, they didn't give me, but I can figure that out because if I know where magnesium is on the periodic table, I can figure out the number of protons because that's the same as the atomic number. So when I'm looking at magnesium, it's number 12 on the periodic table. So what that means is magnesium is going to have 12 protons. The mass number we just said is 25. We get from that representation, and it's neutrons we're trying to figure out. So to figure out the neutrons, we would subtract these two numbers. So 25 minus 12 gives me 13 neutrons. The next problem, very similar. So this is also an isotope. It's just represented in a different way. So this is called a nuclide symbol. So we have the element symbol. This top number is the mass number. So we have the mass number up here. And the number down here, this is the atomic number, or the number of protons. And it's nice when they're set up like a nuclide symbol, because if we have to figure out the protons, neutrons, and electrons, it's set up for us so that we have the protons here, 25. To figure out the neutrons, we take the mass number and subtract the protons. So just draw a line and then put a subtraction sign there. So what is that, 25? 29? So give me 29 neutrons. I don't have anybody in class today, so no one to do these calculations for me. So let me know if I do any of these subtractions incorrectly. So we have the neutrons at 29 by doing that subtraction. We have the protons at 25, which is the atomic number of manganese. And then for the electrons, there's no charge. So that means this compound, this atom, this isotope is neutral. So if it's neutral, the protons have to equal the electrons. Positives and negatives have to equal, so they cancel each other out. So that means if I have 25 protons, I must have 25 electrons. All right. So let's look at the next one, number 6. So this is a multiple choice one. Which of the following best describes phosphorus? So A says it's a non-metal. Well, is phosphorus a non-metal? It's to the right of that zigzag line, and it's not touching the zigzag line, so yes, it's a non-metal. But is it a non-metal that loses 3 electrons? Okay, well, non-metals don't lose, they gain. Okay, metals lose electrons, non-metals gain. So A is incorrect because phosphorus isn't going to lose, it's going to gain. B says phosphorus is a metalloid. No, we just said it was a non-metal, so B is incorrect. C, a metal that has 5 valence electrons. Well, phosphorus does have 5 valence electrons, but it's not a metal, it's a non-metal, so C is also incorrect. Now D says it tends to gain 3 electrons, so that would make it phosphorus with a -3 charge. And that is correct, it does like to gain 3 electrons. To become isoelectronic with argon. So remember, isoelectronic means the same electron configuration, the same number of valence electrons. So if it gains 3 electrons to become P-3, it's going to become isoelectronic with the noble gas in the same row, and argon is in the same row. So yes, it is isoelectronic with argon. So D would be our correct answer for that one. So when you're approaching problems like that, just methodically go through it and look at all parts, okay? Because that first one, all of these are partially correct, but they're not completely correct. So you need to read all parts. Like A said non-metal. Yes, it's a non-metal, but that tends to lose 3 electrons. No, it gains, okay? So read carefully. That's the trick with those ones. Let's look at number 7 now. So number 7 is saying, which 2 atoms are isoelectronic? Circle all that apply. So there might be more than one correct answer here. I just wanted you to get some practice with isoelectronic. So when we try to figure out isoelectronic, we look at the ions given and we write which noble gas it is isoelectronic with, and then we compare the noble gases, and if the noble gases are the same between the 2 ions, then yes, they're isoelectronic. If the noble gases are different, then no, they are not isoelectronic. So AT minus 1. That is way down in row 6. So it is, noble gas is going to be radon, Rn. And now our other option, our other atom, is already a noble gas, Xe. So we compare these two. Are they the same? No. So this is going to be not isoelectronic. Just X it out because it's not. Let's look at this next one, Sr. So strontium 2+. So what that means is we have a strontium alkaline earth metal losing 2 electrons to become a +2. So with the metals, when they lose electrons, they become isoelectronic with the noble gas in the row above. So for instance, strontium is in row 5. So it's going to be isoelectronic with the noble gas in row 4, the row above. So the noble gas in row 4 is krypton, CK(R). And then we have iodine, so a nonmetal gaining 1 electron. And the nonmetals are isoelectronic with the noble gas in the same row. So iodine is in row 5. So the noble gas in row 5, the same row, is Xe. So are these noble gases the same? No, so it's not. Those two are not isoelectronic. Let's look at sulfur. So sulfur is a 2-, so a nonmetal gaining 2 electrons. It's going to have the electron configuration as the noble gas in the same row, which is going to be argon. Now looking at chlorine, chlorine is also in row 3. If it gains 1 electron, it'll be isoelectronic with argon as well. So yes, these two ions are isoelectronic because their noble gas is the same. They're isoelectronic with the same noble gas. This next one, so we have argon, so one of them's already a noble gas, so we just need to look and see what potassium is going to be. So potassium, notice it's a +1. So it's a metal, it's losing an electron. So metals are isoelectronic with the noble gas in the row above, the row that they're in. So potassium is in row 4. So it is going to be isoelectronic with the noble gas in row 3, which is argon. So yes, potassium +1 and argon are isoelectronic with each other. All right, moving on. Forgot number 8 here, left him by his lonesome. What principle states that electrons fill atomic orbitals with the lowest energy first? So that's that Aufbau principle. We talked about Aufbau principle, Pauli exclusion principle, and Hund's rule. So just review those definitions, be able to answer a multiple choice question with them or a fill in the blank, knowing those rules. You will not be filling in an orbital energy diagram where we had those levels, the 1s, 2s, 2p, and then we would draw an arrow up, an arrow down. You won't need to do that for the exam, but you do need to know the rules that you apply when you draw one. And that would be Hund's rule, Aufbau principle, and the Pauli exclusion principle. All right, so number 9, which group has just 1 valence electron? Okay, so it's going to be group 1. So what is group 1? This is where you have to know those common names of the groups. I mean, label your periodic table, color code it. You can use it on the exam. I mean, it's an open book, open note exam. So group 1, with the exception of hydrogen, those are the alkali metals. So B would be your answer for number 9, alkali metals. They all have 1 valence electron. Which answer correctly describes K+? Okay, so it's very similar to that phosphorus one we were looking at, but now it's an ion. So looking at K+, it's an anion with a positive charge. Okay, well remember, anion means a negative ion. Is that negative? No. So A is incorrect. It is not a negative ion. It does have a positive charge, but an anion should have a negative. So B, an alkaline earth metal. So looking at potassium with a +1 charge, it's in group 1. Group 1's an alkali metals, group 2 is alkaline earth metals. Okay, so it is not an alkaline earth metal. So B is incorrect. Looking at C, isoelectronic with krypton. Let's see. K plus is going to be isoelectronic with argon because potassium is in group 4. Since it's a metal, it's going to be isoelectronic with the noble gas in the row above, and the row above is argon. So it's actually isoelectronic with argon. So that one is incorrect. So hopefully D is correct because we've kind of crossed up all the other ones. Cation. Yes, it is a cation. Remember, cation is Ca positive ion. And that is a positive ion. So cation with a positive charge, yes. Is it isoelectronic with chlorine? So chlorine -1. So if chlorine gains 1 electron, it is isoelectronic with the noble gas argon. So they both are isoelectronic with the same noble gas. So yes, they're isoelectronic with each other. So D is correct. All right, let's look at number 11. So this one, you're supposed to circle all the mistakes. And this is just for when you get to the electron configurations and you multiple choice. There might be a mistake somewhere in that electron configuration. So this is kind of practice so that you don't accidentally choose the wrong answer because of some little mistake made halfway through. So let's just look and see if we can spot all of them. All right, we got 1, 2, oops. 1s2, 2, 6, 3s2, 6, 2. This is a big one. Gonna run out of room. 10, 6, 2. Jeez. Probably a lot of mistakes in this one. 5, 10. Okay, so if we're looking for mistakes in that top one, this Kr in brackets, that is just the noble gas shorthand. Okay, so krypton is the noble gas in period 4, so we should start with 5 next. Okay, so that's correct. But 5s1, here's our first mistake. Because if I'm going all the way through the s's, it should say 5s2, because there are 2 electrons, max electrons in the s orbitals. Next it goes down to 4, and this is correct, because when you get into the d's, remember the d's are always 1 less than the row they're in. So if we're in row 5, it's the 4 d's. But notice now we have 4d9, so here's our second mistake. It should be 4d10, because there are 10 transition metals when you count across. And then 5p5. Now there are a max of 6 in the p's, but they could be describing the 5th one. So I can't say if that would be incorrect or not. Okay, let's look at the next one. So we have 1s2, 2s2, 2p6, all good so far, 3s2, and then we hit the 3 p's and there's max of 6. Then we hit the 4, 4s2, 4d10. So I see a mistake here. Remember I just said that these are always 1 less than the period they're in. So if we're in period 4, the 4 s's, when we get to the d's, it should be 3d. But then we hit the p's, so we go back up to 4, 4p6. And we hit period 5, 5s2, 5d10. Another mistake, it should be 4d10, because remember the d's are always 1 less than the period they're in. You hit the p's and you go back up to the 5, so that's correct. we have next. So let's give the electron configuration for an oxygen ion. All right. Key word here, ion. So in order to give the electron configuration for the oxygen ion, we need to know what the oxygen ion looks like. What is oxygen's most probable ion? What charge does oxygen have in an ionic compound? So to figure that out, we look at where oxygen is, and it's in group 16. It's a nonmetal, so it's going to gain electrons. How many electrons? It's actually going to gain 2. Because it's in group 16, it's 2 away from being a noble gas, so it's going to gain 2 electrons to have its full octet. So this is oxygen's most probable ion. So when I'm drawing the electron configuration of this, I don't stop at oxygen. I'm going to add 2 more electrons after oxygen. Okay, let's just start and see what this looks like. So when we draw electron configurations, we always start at the 1s. So 1s2. That brings me to helium. Then I get to period 2. I hit the S's first. 2s2 gets me to beryllium. I'm still in period 2. I hit the P's next. Now oxygen is in the 2Ps. Okay, so if I were going to neutral oxygen, I would say 2p4, because neutral oxygen is the 4th one in. But I need to add 2 more electrons to that. Okay, so what that means is it's going to be 2p6, because O2 minus, that's isoelectronic with neon. So what that means is, since they're isoelectronic with each other, O2 minus has the same electron configuration as neon. So that's what I wrote here. I wrote the electron configuration of neon. Notice it has 8 electrons in the valence shell, 2 in the S, 6 in the P, for a total of 8. So be aware when you're writing electron configurations, is it neutral or is it an ion? Because if it's an ion, you may need to take away or add more electrons. Next, let's use electronegativity values to determine the bond type of the following. So I need to get my tables out.